Last thing to go over. Firstly, thinking about the confidence intervals, as you increase the size of your sample, obviously your confidence interval gets smaller and smaller, which means you are more confident that your mean would occur within a certain range. Okay? As n increases, confidence interval gets smaller, you are more confident that the population mean would occur within that tiny range. Okay? Okay? But there's a question which is basically saying, is it worth constantly getting us larger and larger sample size to improve the accuracy? So because the increase of accuracy is related to 1 over root n, because n is your sample size, n being as that gets bigger, the overall thing is getting smaller. Because it's root m, what you have to consider that if you want to half your confidence interval, half the width of your confidence interval, you'd actually have to do a factor of 4, okay, to half the width. Because if you put 1 over root 4, that's halving the actual overall confidence interval. So is it worth taking 4 times the size of a sample to reduce your confidence interval by a half? Okay, that's one of the things to consider. And they talk about how, with a SAC question that we just did, basically if I wanted to reduce the confidence to only being 0.5 kilograms wide, previously it was 1 kilogram wide with 0.5 plus or minus, but if I wanted to reduce that to 0.5 kilograms wide, being plus or minus 0.25, I would have to take 105 SACs. Okay, so you've got to consider the cost implications of that, the time implications of that, and whether it's worth it. So that's just one of the things to do with large samples. So if I ask you a question about that in the Cambridge exam, or why would you not take a larger sample, but cost and time, okay? To half the confidence interval, you'd need to quadruple the amount of sample, okay? Cool. The other thing is confidence intervals for proportion. So this kind of relates to your binomial distribution stuff and how you can use confidence intervals for binomial distribution, okay? It's the same practice as using normal as an approximation of binomial. Yep. But the things to consider is because it's a sample, you're still going to need your root n situation. And your formulas for things such as mean is NP. You remember NP is your expectation. Yeah, the number times the probability. Your variance is NPQ. Yeah. Yes? Yes? Yeah, cool. So, your standard, when you do your sample, variance of estimated population, you end up with NPQ, which is NP1 minus P, over n squared. Okay? Which becomes P1 minus P over n. I can't remember why it's over n squared, but there is a reason for it. Don't ask me quite why. I'm not going to be able to answer that question just at this second. Which basically comes down to P1 minus P over n. Okay? I think it's probably to do with the fact that P can be m over n. Yeah. Okay? Because that's the number of items which are found to have your characteristic divided by the number of items you have. Okay? So that's how you calculate probability. Success over total. Okay? Success over total is m over p. M over n. So when you put that back into this formula, I think it's something to do with that. But I'm not too sure. Okay, so don't ask me. Basically, you just need to know that these are the equations for it. I don't know if it appears in the formula sheet. Does it appear in the formula sheet? Yeah, it does. They give it to you on the formula sheet. So on the bottom it says approximate distribution of sample proportion. So P just becomes your mean. Yep, for some reason. Yep, okay. And then your variance is P1 minus P over N. You just need to be able to use that so that when you do your proportion, you get these two values here. Okay, so it's for probability plus or minus your standard deviation, whatever it might be, depending on your confidence interval, multiplied by the root of P1 minus P, which is basically the variance square rooted for your standard deviation, over your root n. Okay, because P1 minus P is variance. Okay, so SD would be root P1 minus P. Okay, and then you divide that by root n anyway, so they've just gone, well, rather than doing root top, root bottom, I'm just going to go overall root. Okay, so that's why it looks slightly different to the other one. Okay, and that allows you to do something. So let's have a look at the moths question. Okay, it says, a certain type of moth is found in two colours, brown and white. In an experiment, 100 moths from a particular region are captured. 30 of them are found to be brown, the remainder are white. Calculate the 95% confidence interval for the population proportion. So we're talking about proportion here. We're not talking about like the height or weight, the kilograms. It's about proportion. Proportion is about the size, the discrete size of a concept. Like how many moths would you expect out of an overall population? Okay, that's discrete data because it's, numbers, not they're not measures, they are counting. Okay, so the probability of a moth is 0.3. Okay, based upon this, 0.3 are expected to be brown. Okay, so you do your probability plus or minus the 95% confidence, which is the 97.5% because it's two-tailed. Okay, from your thing, so use the 0.975, which is 1.96, times by the variance over root n, or the standard deviation over root n, which is the square root of variance over n, being 0.3, which is your probability of success, times by your probability of failure over n. Okay, that's it. You just need to be able to use that formula. Type into your calculator, gives you the answer. Okay. I will probably remember why these formulas are exactly the way they are in a few minutes, but right a second, I don't. Apologies. Okay. Any questions about that population proportion thing? So what that gives you is a 95% confidence that the probability of a brown moth is between this value and this value. Okay, so what you're calculating is basically the probability of a brown moth. Okay, your estimated calculation is 0.3 based upon your sample. Okay, but your sample is not necessarily accurate because you don't have the full data. So you're creating a 95% confidence region where you believe the actual probability would lie between. So the probability of a brown moth could actually be 0.25. But you are 95% confident it's going to be between this value and this value. Yeah. So you use a calculated probability with the standard... you use the calculated probability to then find a confidence region. And the confidence region. So you're confident that your probability at 95% confidence is going to be between 0.21 and 0.39. Okay, you're 95% confident the actual probability of a brown moth is between those two values.
Is it kind of the same as what we did, but it's just a different formula?
Yeah, it's exactly. Oh, guys, it's exactly the same as what we've just been doing of the previous questions, except this time it's about proportion and probability as opposed to continuous data, which is about like weight or height or length or time or whatever. It's about a proportion of a population. Okay, it's a different kind of data. It's a binomial data, theoretically, because it's either a brown moth or it's not a brown moth. Okay, and you're counting. Binomial data is discrete because it's just like how many of this actually exist. Whereas the data we've been previously looking is is how heavy is this, which is continuous data, infinite, whereas discrete data is only
Yes.
yes or no, but also real numbers. What's it called? Natural numbers. Natural numbers. Cool. All right.